Hey everyone, what we are starting now is admittedly probably our most challenging unit of the year. It is on sketching rational functions. Now I've taken your feedback and hopefully will incorporate more jokes into this video, but I feel like most of my jokes in class are very natural and come as a result of making fun of you people. And since you're not present while I'm recording this video, then obviously I don't have the opportunity for that, but I really will try to work some in. Perhaps you remember from like simplifying rationals and the few units we did on that, the weeks we spent on that. Rational is like a polynomial over another polynomial. So we're going to be graphing those. They'll mostly already be factored, the numerator and denominator. This is not a unit to practice factoring. There's enough stuff going on in that new thing of this unit. Another important thing to realize is similar to graphing polynomial functions, there's a lot of estimating. We don't necessarily always care about how high or low we go in the y direction. We care more about sort of splitting it into regions and seeing what side it's going to be on. So let's start with just the most basic, y equals 1 over x. And we'll see some strange things going on here. Hopefully I can fit enough in here. I'm not going to write a t-chart down, I'm just going to put it on here. But let's think about some stuff. When x equals 1, y equals 1. When x equals 2, y is a half. We have this point. When x equals 3, y is a third. When x equals 4, y is a fourth, and so on, all the way getting further in the positive x direction. When x is equal to 1/2, y is equal to 2. Right? 1 over a half is 2. I think that's something we're comfortable with. When x is a third, y is equal to 3 for the same reason. When x is a fourth, y is equal to 4. And I think we can see the pattern here. And we would connect it, and it would make this cool shape. We also should consider the negative side. When x is negative 1, y is negative 1. When x is negative 2, y is negative a half. When x is negative 3, y is negative a third. When x is negative 4, y is negative a fourth. And we'll have a really similar thing going on here. You can plug in the point yourself. But we're going to have the same thing when like x is a negative value smaller than 1, what y will become. And we have the following thing going on here. This is the graph. It looks really weird for sure, but some things might make it more clear. The main lesson of this, in a rational function, denominator can't equal 0, ever. We know we can't have denominators being equal to 0. That's something we've talked about last year and this year. So in this case, x can't equal 0 because the entire denominator is x. And we can see that over here, like we're not allowed, we can really come close to this y-axis where x should be equal to 0, but we're never actually going to have an x value of 0. And this sort of concept of a dotted line that a graph can come close to but never be is called an asymptote. And this one we would call a horizontal. No, vertical. Vertical. I do know my left and rights. I promise you that. My brother doesn't know his parts of speech. Like, we're playing Mad Libs. Do people even know what Mad Libs is? We play Mad Libs, and I'm like, give me an adjective. And he goes, is that like a describing word or a doing word? So this is a vertical asymptote. It's a line the graph can never touch, and that's from this denominator not being allowed to equal 0. Perhaps not surprisingly, we are also able to have a horizontal asymptote. If I capitalize the A here, I should capitalize the A here. Y can never be equal to 0. Because even when x goes towards positive infinity, so going all the way to the right over there, y goes towards 0, but is never going to be equal to 0. Right? X could be a bajillion, but 1 over a bajillion is some very small number, not 0. And similarly, when x goes to negative infinity, y also goes towards 0. Right? 1 over negative a bajillion, or however many brackets you could make, whatever huge numbers, x can be as big as it wants in the negative direction. Y will never equal 0 exactly. This graph will only approach y equaling 0, so we get this blue horizontal asymptote here. And these asymptotes are really the key to this whole unit. So I want to show us one other thing here. If we graphed, I'm making enough space here, y equals 1 over x squared. Here the x is squared. Put a t-chart here. When 1 comma 1, x is 1, y is 1. When x is 2, y is a fourth. When x is 3, y is a ninth. Similarly, we will have like the same sort of points here. When x is a half, y is already 4. And you can really write that down if you want to take a look at it. If we square the x value and y depends on it, y will always be positive, right? Even if x is negative 1, y would still be positive 1. If x is negative 2, y is still positive a fourth. So we're actually going to have an exact reflection over here. I drew that poorly, but whatever. Teacher school, guys. Or teacher school. Friends, sorry. So I connect those and graph it. Something I can notice here is I have a similar vertical asymptote, right? Vertical asymptote, which comes from denominator asymptote, which comes from denominator not equaling 0, which means x squared, in this case, not equaling 0, which is just the same as x not equaling 0. So my graph will get really close to that line. But it'll never reach it. And similarly, we said our horizontal asymptote, horizontal is such a long word. Didn't these people realize that Algebra 2 teachers were going to have to write these words one day? The horizontal asymptote is also the same. When x goes towards positive infinity, if you just plug in a huge number in the denominator, y will almost be 0. Similarly, when x goes to negative infinity, y goes towards 0. And that gives us this horizontal asymptote over here. Cool math fact, the name for the infinity sign is not just called a sideways 8, it's called a lemniscate. And I don't know what that comes from. Ask Mr. Miller. Here's a really cool part about this. If you recall in polynomial functions, we said like, oh, when it's squared, right? When the parentheses it's squared, it's going to be like a bounce and not a cross. We have the same thing here. Here this x in the denominator was not squared. It had an odd exponent. So we had this flip of sides. But here, when the x is squared, we didn't flip sides. We sort of reflected, but stayed above the y-axis the whole time. And that is something that is going on there. All right, let's do, again, going to hold this here. Just be able to see the whole thing in the screen now for people to look at. So pause it if you need now. Move on to do a slightly more complicated one. Y equals x minus 2 over x plus 4. We're going to skip really straight. We're already given up here of plotting points, and we are going to talk about the shortcuts for doing this sort of thing. First thing we want to think of is, what color I've been doing the vertical one in? Red. First thing we want to think of is the vertical asymptote. And I know asymptote's a long word, but there's a good reason we can't abbreviate it, okay? We don't want to have a... Never mind. You guys can figure that out. You're in 8th grade. So a vertical asymptote is when the denominator can't equal 0, which in this case would be x can't equal negative 4. I get mixed up with vertical and horizontal, but like, we'll figure it out, okay? X can't be negative 4. Right, this is the point x equals, right, this is when x is negative 4. We're going to draw a vertical dotted line going through it. That's the method there. What I want us to think about now is kind of strange. That, actually, something we should also think about while we're talking about it, I'm going to run out of colors, is first, the second thing we would do would be to find the x-intercept. From before we know, even from a line, right? X-intercept is when does x, okay. Let me try to think about the best way to explain this. The x-intercept occurs when y equals 0. Right, when y equals 0 and we have no height, that's the x-intercept. Y will equal 0 means the numerator equals 0, right, because the denominator can never be 0. For y, the whole left side, y to equal 0, the numerator has to equal 0. So in this case, that's x equals 2. So let's plot our x-intercept there. That was a kind of clunky explanation, but hopefully it makes sense. Shortcut is x-intercept is when the numerator equals 0. That occurs at x equals 2. Third thing we could graph, and I am running, orange. The y-intercept, we should know occurs when x equals 0, which in this case would give us y equals 0 minus 2 over 0 plus 4. So you got to plug in, and you would get negative 2 over 4, or negative a half, right? Yeah, negative a half is our y-intercept. That's what we have going on there. What do we want to talk about now? I've been using the blue. I've been saving up because we've been using blue for the horizontal asymptote. This one's kind of tricky. The horizontal asymptote, if you recall from the previous examples, is when x goes to infinity or negative infinity. So I want us to think about it this way. X goes towards positive infinity. When x goes to positive infinity, y equals infinity minus 2. Let me try to draw this better. Right, I'm really plugging in infinity for x, which is kind of questionably allowed, but it'll get the point across. Over infinity plus 4. Okay, take away 2 from infinity, still infinity, essentially. Take away, add 4 to infinity, it's still infinity. So I'm going to simplify this to infinity over infinity and equals 1. So when x goes to positive infinity, y equals 1. Maybe if you want to think about this as a number, imagine if x was a billion. A billion minus 2 in the numerator over a billion plus 4 in the numerator, or in the denominator. Well, the numerator and denominator are still very close to each other, and y is going to equal approximately 1. And that will only be more true as x gets bigger and bigger and towards infinity. And the same sort of thing is really going to happen at x going towards negative infinity, because we can see y is going to equal negative infinity minus 2 over negative infinity plus 4, which will just be negative infinity over negative infinity, which is 1. So at y equals 1, I draw a horizontal line. All right. These are the 4 things we got to put on first before we can do some sign analysis again. And that's thinking about it in terms of different regions. In polynomial functions, we said we could only switch across x-intercepts, right? We would split it into regions based on where the x-intercepts were. Here, we also have to split it into regions based on vertical asymptotes going up and down. And doing this example will hopefully make it clearer. Start with the region which is all the way here and to the right. So, when x is greater than 2, y is going to equal a positive number in the numerator, right? If x was bigger than 2, that x minus 2 will be positive, and adding to 4 will also be positive in the denominator, so overall positive. That's how I graph that black line right there, that black curve. By realizing that when x is bigger than 2, y is positive. This is what we did essentially in polynomial functions. Now we just have a denominator to think about also. But this is something we should be cool doing. Please ask me about that. Now we can't just say the rest of this is to the left, because what I said is we have to deal with a region of, actually I made that too tall, but you'll see why in a second. We're going to have to deal with, let me think, because I also want to show that it's going towards this asymptote, but never crossing it and never touching it. All right, I'll let people catch up because I did a lot of erasing. Even when I have time to plan it out and do a video, I still do that, okay? Nobody's perfect. What I would have next, we might think, oh, just the region to the left of that x-intercept. But no. What I need now is a region where x is between the x-intercept and this red dotted line. I need to create new splits of regions at vertical asymptotes also. So that would be when x is between -4 and 2, right? In this region, in between the red dotted line and the green dot, x-intercept. When x is between -4 and 2, my numerator is always going to be negative. And I encourage you to pick a random number. Even if you go all the way up to 1.999, right, it's going to be a negative numerator after you plug in x. But the denominator will always be positive. Even if I go to x being a negative 3.9, adding that to 4 will give me a positive denominator. And then a negative divided by a positive is a negative. So I want to erase this arrow now because it's going to get in the way. So sorry. Here, y will be negative, which means the value of the function will be below the axis in negative land. Best place to visit, cheap tickets. That's how I graph that. That's really, I really cannot stress enough, similar to polynomial. Polynomial functions, we would have said, oh, this, it's positive on this side of the region, and then we're going to cross the x-intercept and go to negative on the other side, making sure to go through the y-intercept also. The only other thing we need to think about is these asymptotes. It needs to approach them with its arrows, both the red and the blue, the vertical and horizontal, but never touch them. All right, let's do this region in the corner here. When x is less than negative 4. Anything to the left of negative 4, that's what we're plugging in now. The numerator will be negative. This will be negative. And overall, that will be positive. So y is positive over here. In this little corner, how am I going to graph that? As follows. Because y has to be positive, right? The value of the function needs to be above the axis, but it's sort of trapped by these asymptotes also. Right? If it's positive, it's going to start like very close to these asymptotes, but it'll never reach them, and it's always going to maintain positive the whole time. Visualize how this looks really similar to the 1 over x we originally graphed, but just sort of the center, the intersection of the asymptotes, was dragged to over here. I'm going to leave this up. We are going to graph 2 more. And again, when we work on this in class, that's why we're doing these videos, so we can get practice all together and really just like have review days every day for this unit. All right, we are graphing now, and I'll try to draw it better so I don't run into everything. The following rational function. All right, I made that 5 by 5, if you want to know my axes, or 10 by 10, 5 in each direction on each side. Let's go through some steps here. I think I've been doing red for this, so I'm forgetting. The vertical asymptote occurs when any value of x, I would make the denominator 0. In this case, there's 2, right? If x equals 2 or x equals negative 4, we would get a negative denominator. I mean a 0 denominator. Sort of like doing ZPP in the denominator, right? If one of these parentheses equals 0, the entire denominator will equal 0. So we actually have 2 vertical asymptotes here. Our next step would be, I made this green last time, I think, would be the x-intercept. And I said the shortcut is for the x-intercepts would be what makes the numerator equal to 0. And in this case, that would be x being 3 or negative 3, right? ZPP with the numerator there. If I have x equals 3 and negative 3 on there. Wow, honestly, I have no clue how I would have taught this in class and not in a video. Y'all would have been screaming about a lot of things. Though I have the utmost faith in you. Don't worry about that. The third step is the y-intercept. No, I did not do that in blue last time. I did it in that pretty orange. Which is when x equals 0, and if we plug that in, we get 3, negative 3, negative 2, and 4, which equals 9 over 8. So, whatever fraction, but plot 9 over 8 well enough, approximately, of course. There's so many good colors on this. Horizontal asymptote. Which is when x goes to infinity. We're going to have a really similar thing here. When x goes to infinity, something we would see would be y equals infinity plus 3. I'm going to run into some issues here. Also, it's almost math lab. I hope nobody comes and I have to pause this. And I don't know what to do that on this computer. Infinity plus 3, infinity minus 3, infinity minus 2, infinity plus 4, right? Same logic as before. All of those parentheses would be like infinity. Infinity plus 3 is still infinity. So I'll actually then get this weird thing of infinity squared over infinity squared. Point is, that still equals 1. So I have a horizontal asymptote. Here. And my next step would be to think about crosses and bounces. So let's, like, is it going to be above or below? Let's think about the first region, all the way to the right. When x is greater than 3, so anything to the right of this. When x is greater than 3, y equals positive first parentheses. Next one will still be positive. All positives. Right? This is all positive. So it's going to start above here, approaching the asymptote but never touching it. The next thing that could happen, I'm going to kind of fudge this already. We know from polynomial functions, if it's not squared, like if the parentheses, the factor that gave us this x-intercept isn't squared, it's going to cross. This comes from the x minus 3, right? That's why x equaling 3 is an intercept. And that is then going to be a cross and not a bounce. That's the same logic as our previous unit. So I'm going to cross it. And it's going to go over there. That's from before. Crazy trick also. The cross bounce sort of thing works the same as an asymptote, except it might more accurately be described as a flip or reflect. I want us to go look at the first page of this for a sec. this asymptote, this x gave us this red dotted asymptote. The exponent of this x is odd, so it's a flip. This x squared gave us this red exponent, but it's squared, so it's a reflect. Squaring, just like polynomial functions, means a bounce, staying on the same side. But a not squared means a move to the opposite side. So if I was negative over here, when I flip to this region, which comes from the parentheses x minus 2, gets me the asymptote at x equaling 2, I'm going to flip and start positive. Right? I'm going to start somewhere positive. Now, and I know that because I don't bounce. This is like a cross, right? Moving from negative to positive. This is where things get a bit funky, right? Coming close to the asymptote, not touching it. Gotta go through the y-intercept. A y-intercept is not a region change. Neither is a horizontal asymptote. So I need to reach this x-intercept. The only way I'm going to do that is by going through the horizontal asymptote. Horizontal asymptotes can be crossed. We're going to talk more about that later. But really what that means is there is an x value that would give us y equaling 1. We could solve for it. We're not going to. But visually we can see we're going to have to cross it to get to that x-intercept. So that's whack. Next, an x-intercept means a region change. We have to determine cross or bounce. This x-intercept comes from the parentheses x minus 3, which is not squared, so it's a cross going close to the asymptote. We got to decide, red dotted line, vertical asymptote, cross or not. Like switching or staying negative over here. That comes from the parentheses in the denominator x plus 4, which is not squared, so it's going to switch to positive. So that's what we have going on here. It's so pretty, guys. I don't know. Could hang in a museum. I mean, I think it could work. I'm sure all of yours like beautiful as well. All right. Thing to do next. Let me leave this up here to pause. All right. Gonna do one more, and it's gonna be our most complicated yet. But now that we know all of these shortcuts, it shouldn't be as bad. X plus 4 squared. X minus 4. X plus 2. X minus 2 squared. You can see here we have something in the numerator and something in the denominator squared. And we're going to see how those play in. That's really the point of this example. We make some axes, 1, 2, 3, 4, 5. That was a weird way to make axes. Don't do that. Don't look up to me. I'm a poor role model, and they're so not straight. All right. What have we been doing first? I really should remember. I should have written it down. Vertical asymptote first. Which is when the values of x, I would make the denominator equaling 0, which are x being negative 2 and x equaling positive 2. Really important, we will see the x equaling positive 2 comes from this factor, which is squared. Have to have that in mind. But first, let's just dot these on here. Sometimes I wonder, what even is math? You know, just like, this is all made up, but whatever. Don't tell Mr. Silverman I said that. green, no, green, we've been doing next, yeah, for the x-intercept, which is what makes the numerator equal to 0. Numerator equals 0, ZPP, the numerator, essentially, when, oh no, I got it back. Guys, I think for the most part, my technology has really improved. X equals 4 would make the numerator 0, or x equals negative 4. Important to realize this, x equals negative 4 is an option for 0 because of x plus 4, which is squared. So keep that in mind as we graph x equaling 4, x equaling negative 4. And now the best part. You're all gonna like y-intercepts the best. I wonder whose is the most colorful. But orange really is the best thing. Especially since you'll be watching this right after opening day and my beloved Orioles. Orange, of course. Y-intercept is when x equals 0. Let's plug in 4 squared negative 4 over 2 negative 2 squared, right? When x equals 0, it's just like gone. This was not math I did yet, but let's figure it out. The numerator would become negative 64, and the denominator would become positive 8, right? So the whole thing is negative 8. Oh boy, I did not draw this axis far. This is what happens when you do an example for the first time as a part of the notes. That's probably something they tell you not to do in teacher school. So gotta extend these big time. I hope you didn't start this at the bottom of a page. And it's really not straight, but you know we live. Let me just make sure I did that right. That seems like a lot. The numerator would be 4 squared is 16 times negative 4 is negative 64 all over. Okay, fine. If anyone catches a mistake, tell me, but it looks right to me. 1, 2, 3, 4, 5, 6, 7, 8. Great. Maybe we should also extend these asymptotes then. Alrighty. Green here for, no, blue here for a horizontal asymptote, which is when y equals, when x equals infinity, what happens? Or as x goes towards infinity, right? We can't really use infinity algebraically. I'm doing a lot of cheating in here. Like with the negative 1/12 thing that I showed. Y equals infinity plus 4. Squaring that's going to get us infinity, right? Infinity plus 4 is infinity. Square that, I'm just too lazy, and it makes the video shorter, guys. We should be able to realize that's going to be infinity squared. Infinity minus 4 is infinity. All over infinity times infinity squared. You can ask me in class if you don't know where I got those from. It's going to simplify to equal 1 again, right? If x is a huge number, plug in 1 billion on your calculator if you want to. The value of y would equal 1. Let's do a lot of shortcuts to figure this out. Thing that I think is best always is to start in the region all the way to the right. So, when x is greater than 4, y equals positive squared negative positive and the negative, oh no, that's positive. Sorry, oops, catch that. First parentheses is positive, and it's squared. Second parentheses is positive. This is also positive, sorry. They're all positive if you plug in any number beginning 4. So the squareds, I just put them where they were. It's going to overall equal a positive over a positive, which is positive. So when x is to the right of this green, it's going to be positive. Now we got to determine cross or bounce. This green dot came from the parentheses x minus 4, which is not squared. From the polynomials functions unit, we know that is going to be a cross then. And again, going towards asymptotes, but not touching. I mean, we should know by now, you really can't just touch someone's asymptote, okay? It's not cool. Mr. Walkinshaw made that joke to me in 8th grade, so I know it's at least somewhat appropriate to say in class. No, that's not actually where the word comes from. Okay, gonna use the same logic here, and this is gonna be weird. This asymptote, this red dotted line, comes from the parentheses in the denominator of x minus 2. But it's squared. So instead of crossing to over here, which I'm not gonna do, I'm gonna go over here. And stay negative. Another way I can think about this is like in this region from red, between the red dotted lines, I have to touch this orange dot. That's on the graph. It's the y-intercept. I'm not going to do that successfully if I'm stuck up here. So it's going to be, right, just cross. Well, I don't want to use the word cross because we use that to mean a different thing. It's going to reflect across the asymptote because the parentheses that gives us this asymptote in the denominator is squared. It's going to start negative. And it's negative this whole region, right? That's what this tells me. So it's not like going up past the axis. So it's way down here. This sort of upside down parabola is shape. Just chilling there by itself. All right. Next region happens at this asymptote, which comes from x plus 2 in the denominator. Not squared. So it's going to flip its side and start over here. In order for it to get to this x-intercept, it is going to cross the horizontal asymptote, which we've already thought about. Perhaps an extra credit question could be about figuring out where that happens exactly. And wait, how did that happen? All right, this is a weird thing. It's about to happen. Okay, I do remember this. This x-intercept, oh, this is so cool, comes from, right, x equaling negative 4, comes from the parentheses x plus 4 in the numerator, which is squared, so it is a bounce. It's going to look like this when it bounces. Let me try to clean that up and extend the blue dotted line. When it bounces, it's not going to cross this asymptote again. It's going to be going really alongside it in this fashion, which is funky, but happens. We really are only crossing it once. Again, we're not going to talk so much about that, but that's what's going on there. So I'm going to leave this up here. There's a lot going on. But I think really this process of 1 through 4, then the regions and the shortcuts, is the best way to do it. And again, we'll get a lot of practice in class tomorrow. So I'm going to end the videos here. I don't know if YouTube can handle me uploading a huge video for the entire unit. Videos for this unit are kind of long, I know. Hopefully the jokes made it at least tolerable and the math made it especially exciting. So the other lessons are going to be separate videos. And now we always have to determine, do I know how to